we forget. All right, and turn off my phone. Good. So, so Apache Spark, which was done around the end of 2013, is very a fast and general engine for large-scale data processing. Basically, it is for the processing, for the computing, not for storage. So it's more like a compute engine. It's really, really fast in the sense that if it is done in memory, is 100 times faster than what Hadoop does, Hadoop's batch job does, and 10 times faster when it's on the disk. So Apache Spark can be run in can load the data in memory, or we can mark that the data should be partially in the disk. Okay, there are multiple modes. And even on the disk, it is faster than Hadoop's MapReduce. All right, and that is the reason probably why we people suspect that the second part basically that is the reason why people suspect that it will replace MapReduce. All right. So before we compare, let's go into the details of Spark. And once we have a fair idea about Spark, and you already have a fair idea about MapReduce, you can deduce your conclusions. All right. So it builds on the similar paradigm like MapReduce and is integrated well with MapReduce. All right. It's basically integrated with Yarn. So this is the general diagram representing what Spark has to offer and on what things Spark depend upon. So Spark's core is something which we are interested in, and Spark's core can be run as a standalone scheduler. It can run on top of Yarn, and it can run on top of another resource manager called Mesos. Okay. So on top of Spark Core, you have mlib, GraphX, and Spark Streaming. S- So Spark Core is the one which is the compute engine on top of which people have written libraries. The way we have in Hive, similar thing we have Spark SQL. Oh, audio is breaking. Mark? All right, so let me have a. All right. So if the audio breaks, then I'll set up something else. So no worries. Today I have all the backup plans. All right. So Spark can either run as a standalone scheduler, or it can run as on top of Yarn, or it can run on top of Mesos. And on top of Spark Core, we have various libraries that utilize Spark Core, just like we would be using Spark Core. There are other libraries which use Spark Core to provide you various functionalities. So first of them is Spark SQL. Spark SQL basically instead of Directly dealing with Spark, you will be talking in terms of SQL, and that would be converted into the way we were converting into MapReduce. Similarly, here our SQL will be converted into transformations and actions. All right. Now, Spark Streaming is a real-time processing tool. So this we will go into the basics of Spark Streaming, and mlib will not be discussing here because that is little too advanced for this session. And GraphX is for graph processing. All right. So okay. So the first step to get started is install it on the yarn. Download the Hadoop 2.4 version of Spark, and once you have downloaded, you basically extract and and then start running. These two steps are basically copying it to user lib and then renaming or linking it with Spark. Okay, so linking these two folders is Spark and this. So the path looks really clean. Instead of saying user lib spark dash 11, we are just simply saying Spark. So once you are done with that, you can simply type this command user libspark bin and pyspark. So we'll be going ahead with Python Spark. The reason is that if you're getting into big data, it makes more sense to go with Python because lot of tools and technologies are in Python. Okay. For example, in case you are going into the domains like R, it makes sense these days whatever you can do in R, you can basically do it with Python by using a library called Panda in Python. So so basically whenever you are dealing with big data or any similar domain where you are extensively manipulating data, Python seems to be a logical choice. Okay, so that's why we did not go for Scala. We went for Python, and mostly in our classes, 1 out of 10 people there are though they know Python already. All right. So is the voice okay now, or is it still breaking in between? Mark, good, good. All right. So yeah, let's first try to run Park. We have already installed for you, so you can go into the command prompt and then start. So you SSH onto our server and you know the password. I'm hoping if it is not there, you can see in the installation document in the session one and in the installation document in the LMS, and you should be able to log in. All right, now I'm logged in into our server. All right, here we have. Let me increase the window. Great, great, and so all right, so we can say user lib and spark and then bin and pyspark. All right, so a little bit about this command prompt. Okay, so you will see this prompt. It basically says it's a Python version and the context is available as SC. So if you look at it, if you generally launch a Python, you have the same prompt, exactly same prompt, not much of a difference. All right, it has not much of a difference. It's exactly same, right? Except for the banner, the few things here. All right. So The only difference with PySpark and normal Python prompt is this object called SC. SC is an extra object provided to you on this prompt where is basically the interface or the gateway to the Spark. So if you want to deal with Spark, you start with SC and onwards. Otherwise, if you don't use SC, Spark context, you can continue to use as if it's a normal Python prompt. So this is so Sergio had just joined. So let me bring him to the session also. Yeah. So so basically, to launch PySpark, you can use this command. All right, you can use this command, and it will launch you the the command prompt here. So basically, it's nothing more but it's normal uh, Python command prompt. So here you can say things like my variable, whatever variable you want to define, 3 plus 4, and then you can see the value of a variable just by typing here. Similarly, you can define a function, or you can call a function. Say you have got an array a equals 1, 2, 3, 4, and 6, let's say, and you can see that this is an array, and you can say array dot sum. I think not sum, it's simply sum. Yeah. So you can see this, we can call the functions on this, such as length. This is a normal property of Python. Yes, that's correct. Because the community around Python is going to be more. So I'm responding to Mark's point that plus there are a lot of tutorials on PySpark. That's correct. All right. Now here you can basically call any function. Also, if you want to define function, you can say def my fun is x comma y, and what does it do? It just basically returns x divided by 1 dot x divide by x plus y, or we can further make it something little more uh, complex, such as x minus y. All right. So this way we can define our function, and if you want to call this, if we want to basically run it, so it is going to be uh, define this, and all right, we have to say return instead of saying that. Okay. Now you can see that it has returned 3 plus 2 divided by 3 minus 2, which is 5. All right. So we have just created a function. So this is a normal Python command prompt. Now, if you want to use SC, all right. So the first thing you would do would be load some data. All right. So let's start with understanding what does it mean by loading the data. All right. So the most important concept around which the whole Spark revolves around is the concept called resilience distributed data set. Basically, it's a representation, just like an array of a very huge data. So you can think of an RDD as if it's a huge array of elements which is spread across multiple machines, which is spread across cluster. So you have got a huge array. Every RDD is a variable. RDD is like a data type. In terms of programming, Python programming language, it's a data type of an object which essentially represents an collection of elements which are spread across the cluster. So an RDD is essentially A resilience distributed data set is basically a representation of elements spread across the cluster. Okay. Now, this data could be anywhere. Under the hood, it could be normal file system. It could be it could be in the HDFS. It could be at various places. So Spark provides you a way to load this data from various places. Okay. And in case you are using Yarn, it will make sure that the cluster, the nodes that load your data are on the same machines containing the data. Okay. So basically, so here you can see that the way I have represented it, there is an HDFS underlying the file system. When we this is just an example. You can convert a normal variable in memory variable into RDD. We will show you that, or you can load the data from other file systems such as DFS. And RDD is basically, you can think of it as there are multiple nodes, one, two, three, four here, containing our data. All right. Now, the other properties of RDD is it can be persisted in the memory, meaning if you have multiple processes running and you want an RDD to stay and be shared across multiple processes, you can persist in the memory. As well as RDD has the ability to recover from failure. It is fairly resilient. So in case one node goes down, you can that in case one node goes down, the the same partition of the element is are shifted to another node and it is brought into life instantaneously. Okay. So generally, each element can be any object, or it can be that there are two things. Either the object can be just an object, or it can be in the form of key and value can be object. So these are the two general types of this array. An RDD, you can visualize it like a big array containing either the objects or key value pairs. Okay, each object is a key value. Now, every RDD supports two kind of operations. One are categorized as transformations and other are categorized in action as action. We will talk about these two in a minute. And every element of an RDD across the cluster is run through the transformation, and this example of transformation is a map function. We'll talk about this in the next slide. But let's load our data. If you remember, if you remember when we did the word count, this is the file we used. Okay, this is the file we used. So, all right. So as I was talking about, the SC is your gateway. The Spark context is the gateway to the to this file. Okay. It's a gateway to this file, and this command prompt is a Python command prompt. And so what this syntax is doing, it's saying lines equals sc.text file, and then the URL. The URL contains the protocol, and based on this protocol, Spark figures out how to load this data. Now, if you want to load a text file, this is the common format. All right. So what you can do is this basically would create an RDD called lines. So here, why is it that I'm not able to paste? So, okay, for some reason I'm not able to paste. Or is it something to do with my... Oh, copy paste is not in general working. It's not working. So Is it not working for anything, or is it not? Yeah, here it's working. Here it's working. It's just the keynote is not copying. So let me restart the keynote. Are you guys with me, or is there a doubt at any point? All right. So let's just try to load it. Let's just try to copy first. If it is working now, yeah, this time it's working. All right. So yeah. So here what we have done is we have said Spark load these lines as the day. So now it has loaded our file from HDFS, and you can check that. And the moment we run PySpark, it actually figured out that we are trying to run on Hadoop and connect it to our normal system. All right. And there we say, just let me check if it has really got the correct data. So I say lines.take, and it will bring 10 lines from the resilience dataset. Okay. So yeah, it's the correct one. It's a Project Gutenberg's The Adventures of Sherlock Holmes, all the books. Yeah. So lines contain all the books. Now we can now we can also load any of the in-memory variable, such as, let's say we define our variable as an array of few numbers, right? And let's say this is 4, and this is 8, and this is 9, right? And if you want to load as RDD, we can say some variable, whatever we want to say. Here we are saying VRDD equals sc dot parallelize. Parallelize. Okay, that's a very difficult spelling for me. All right. So this way it has created a variable, and here we can say take 5, and it'll give us the result. All right. So it has taken our array that was V. This syntax has taken our array, which was an in-memory variable, spread it across the cluster, and afterwards it has gen- given us a handle to the RDD. So VRDD is a handle to to an RDD. Okay. So you can check that what exactly is VRDD. It will tell you. So you can say VRDD. It says it's a parallelized collection RDD. Okay. Under the hood, all of these lines are being converted into Scala, and that is how it is. All right. So this is how you can load any data, whether from in memory or from HDFS or from network file system. Howsoever, you can load the data as an RDD, and then you can start applying the transformations. All right. So whenever we are loading a text file, the new line is the separator between elements of an RDD. So each line is an element. So if you say line dot take one, okay, so it is essentially the first line. Or if you say 10 take 10, so each element of this RDD is basically basically this. You can see each element of the RDD is a single line from the text file. All right. Now, next step towards this is transformations. Now, we have created RDD. We can apply a transformation on top of it, or we can apply we can apply an action on it. Okay, just like we had map reduce kind of paradigm in. Okay, just like we had MapReduce kind of paradigm in MapReduce in Hadoop MapReduce. Here we have transformations and action. Okay, a transformation is something which happens on each node. Also, transformation is like a translation, converting. each element of an array into something else, or converting these elements on each node into something else without bringing them to the launcher box. Here is Spark driver application. Right now, the command prompt, that is our node which has launched this command, is the Spark driver application. Here, this command prompt right now is a driver application, and we are commanding Spark from here to do things for us. We said load our data, and it loaded the data onto the cluster. And next would be we apply a transformation. So it will note down that you have applied a transformation. And the moment you do an action, whatever transformations you have applied so far will be will be executed. Without an action, no transformation actually executes. Just like in pig, until we did store or we did dump, none of the commands on which our data set depended were executed. The moment we said dump something, everything on which that something was depending was dumped. In the similar fashion, the moment we do an action, everything on which that action is going to depending will get executed, including the transformation. All right. So transformation essentially is that converts an RDD, one RDD into another RDD. One resilience dataset into another resilience dataset. There are multiple kind of transformations. We will talk about each one. And before we go ahead, let me yeah. So so a transformation essentially runs on each node and translates one RDD into another. There are multiple transformations, starting with a map. The map here is a little different from what we have understood so far. A map here is something which just converts your array into another array, or your RDD into another RDD with the same number of elements as the original, but but after the transformation has been gone through this function called func. So if you this essentially, let me reiterate what I'm trying to say. When I say my RDD1 dot map func, what is it going to do is it will take this function, a func is basically a pointer to the function you have just defined, and what it would do is it will take this function, apply to each element of this array or this resilience data set, and generates another data set. So let's have a quick example here. So we talked about V, right? And we said there is something called RDD V1, VRDD, right? Now VRDD was representation of our V in the form of RDD. Now we say, let's say we define a function called cube. Okay, define my cube. All right, and what does this do? Or let's say, do we have a square here? A square? No, we don't have a square. So let me just define cube here, and I say cube, define cube, and whatever value we have, we return x into x into x. So now we have defined a function called cube. We can test whether it's working or not. We say cube 3 is working fine, cube 0 is working fine, and cube 2 is working fine. All right. So what we want to do is we want to apply this cube function on each of our elements of an array. Okay. So VRDD, that is the RDD representation of our V. We have copied V onto the memory into the RDD, and what we want to do is map, and we pass the handle to our function, and let's call it uh, cube cubes. Okay, we give so cubes is another RDD being generated as a as part of this operation, and you should notice that when we executed it, it did not take any time, meaning There's nothing has happened so far. And the moment we say collect, okay, if you want to see all the values, we say collect, okay, and we will get a local array this time, and we say cubes all equals this. So this will basically bring everything locally and into a local variable. So you can see that cubes contain all the cubes. All right. So basically, it took our cube function. Again, have a look at this statement, not this. It took our cube function and applied on each element of our RDD, generating a new resilience dataset, which we can anytime pull back to the node using an action such as collect. All right. So, so is the idea about map is clear to everyone? Any doubts? Great. So that is our map function. That is our map function. Now, but the problem with map function is that it has to generate another value. Either maybe null, but it has to generate a value. So it is one-to-one mapping from input to output. And all the function, when we define a function here, function can only take a singular argument. Or function has to take at least one argument. Or has to take only one argument. Now there is another kind of transformation called filter. If we do not want certain element of an RDD to go into another set of you don't want certain elements of an RDD to go into the another RDD, then basically you apply filter. For example, let's say whatever we got in the previous uh, in cube all. So what was the okay? So in the cubes, we want to say we want to filter. What kind of filter do you want? Let's say divisible by 2. We only want in our output that only the elements which are divisible by 2 should pass. Okay. So let's define a function called is divisible by 2, and here is our function. What it does is if if x percentage let me just put brackets. I'm not that great with Python because of my bad habits of Java. Okay, so the moment we see that it's divisible by 2, we say return true, else return false. Okay, so let's test if our function is working fine. And let's say 1, so it says false, 0 it says true, it 2 it says true, 4 says true, and 41 false. Perfect. So our is divisible by 2 is working fine. Now out of these elements cubes, what we want is we take these elements cubes dot dot say filter, and our function is this. So we are saying out of cubes is remember cubes was our RDD containing cubes of all the values, and cubes dot filter basically would let only the elements the we will it will let only the elements which qualify for this function go into the output. So we can say uh, only even. Okay, Now, if you say only even and you say collect, you will see that so only the even cubes has come out in the output. The moment we said collect, it executed the process and gave us the result. And you can see that it's fairly fast. Sounds good to you? All right. So a quick question to you, a quick question to all of you is is so if we have a equals to and we say or we can say b equals to a dot filter and some function, length of a is greater than b, greater than or equal to b. True or false? True or false? Anyone? Mark, Anand. Samantha say, Santana says true. Mark says true. And Anand and Sarju. So we apply filter on top of A, and this syntax means we take a function, we check against each element of A, and whatever element are returning true when that element of A is passed to function. If function returns true, that element goes to the output. Otherwise, the element is not put in the output. So we basically filter some of the elements from A into B. So Anand, so yeah, it is correct. It is true. So length of A is either bigger, A is either bigger or equal to B because B is always a subset of A. All right. So that is filter. Next is your filter map. Filter map. So filter map does nothing but takes the function takes the function, applies to each element of each element, and there each element can generate as many output as it wants. Okay, each element can be converted into multiple values. Okay, and and then right, so each element can be converted into many values. Okay, so let's see if we can define a function. Define let's say flat map example, and we give it a value x, and we return three values. Return x minus 1, x, and x plus 1. Okay, so if we give it 1, it will return us 0 1 2. If we give it 2, it will return us 1 2 3, and that's it. So let's say that whatever values we got in the previous step, or we just say vrdd. So vrdd dot flat map, and we pass the function like this. Okay, and we just generate called fmr flat map rdd. That's what I'm trying to say with these variables, and fmr dot collect. So so you can see that each of the values, so so what was in the v, So 1 has been converted into 1, 0, 1, 2, 3. 2 has been converted into 1, 2, 3. And 4 has been converted into 3, 4, 5, and so on. So everybody with me here? Great, great. So, so we were able to convert one value into more. Or we can also say that I don't want to return any value. All right. In case our function was something like this, whatever value you pass, it is returning nothing. Okay. So, and we pass that into our function here. And let's say this is fmr1. So effectively, the whole array will become empty. All right. So basically, in the flat map, we return this function which we are passing to flat map can return any number of elements for each element. Okay. For each element you pass to this function, it is choice of this function, and this function will be written by us. It can return zero or more values as per its choice. Now you recollect our discussion of normal map reduce. The normal map reduce convert basically return the map function of our map reduce generated any number of keys of our choice. So flat map is very close to what we talk about when we basically when we talk about normal map reduce, flat map is very close to that. All right. Also, every element can generate a tuple, which is a key value pair. All right, we'll show you that part. So if our function was something of this sort, so let's say we are defining a function which does nothing but converts it into key value pair. Okay, so if we pass something to it, say f10, it is going to return something of this sort. All right, and now let's apply it onto our normal VRDD. Now this time fmr1 will have something of this sort. So uh, so here these elements have are basically key value pairs. Okay, okay. All right, so something background jobs are running for this. Yeah, this is more like an R. That is why, Mark, lots of people have realized that since R was anyway showing its age, so what people did was they took R and and wrote the similar thing called Panda, and you can start using it exactly like R. So that was the benefit of having Python command line. Python was not the only one which provided command line. There has been others also. Probably it all started with R. So yeah, for the rapid programming, these commands are really useful. Okay, so whatever power we got from R, so people had written the similar thing here, so that power of R could be utilized. So it's great that you use R, and basically you will be more benefit and you can more closely connect with these tools. All right, great, great. So now we will go into a little bit more details about. So this is like a rapid work. You keep on you give some input, it gives an output. All right, rather than a batch wise where you program, submit, and when it finishes, it'll let you know. Next kind of transformation is group by key. Okay, so here there are keys here, and we can say uh, fmr dot group by key, And right now we are not saying anything else, and we say group equals this. And if we say group dot collect, let's see what is there inside it. So it says that the int object is not iterable. All right, just a second. Oh, okay. So the fm1 is not really a key value pair. So this was flat map, fine. Then we had, yeah. So we had this function called f, and f, anything you give it to f, it returns these things in this format. And we had vrdd1, vrdd1, vrdd was this. And then let's say we say map, and we pass a function here. And we say, what exactly are we trying to do? We are trying to, just a second. So we have got a function which is basically converting it into key value pairs, and we say vkv equals this, and vkv dot collect. Yeah, now you can see that our object is basically our object is in the form of key value pairs. And now on top of it, we can say easily that we can do a sort of group by on top of it. All right, so we'll do group by later, but if you want to try out group by key and do nothing here and say this is my group, and group dot collect. Okay, so group dot collect is basically a for each object it has grouped by key and generated an array. This is an array representation. All right, so it's not easily serializable here. That is why you are seeing. Now, after you have done a group by, so group by basically groups the whole array or RDD by the key value. But before doing group by, you need to have the data in key value format rather than simply values. All right. Otherwise, it will give an error which we got earlier saying the object is int, not key value. Okay. So there are multiple transformation. Map simply maps converts one value into another in an RDD. Filter creates another RDD out of few elements of the existing RDD, those qualifying ones based on your function definition. Flat map generates multiple key values, multiple elements for each element, and the map first one basically not only converts one value into another, you can also convert one value into key value. If you put round brackets around a value and say a comma b, you generate a as the key and the b as the value. All right. Group by basically groups the data by key. All right. But for that, first you have to do a map and generate key value. There are far more kinds of transformation, such as sample, union, intersection, distinct, group by, reduce by key, and so on. All right. Now, so we will go into the details of each one example, and then you will get more hang of it. But are you comfortable with all these four elements, four kind of transformation? So I'll answer Mark's question soon. So Mark's question is, do I have to install Panda or is it part of PySpark? So you have to install Panda. Panda is not part of PySpark. Panda is a general library of Python, and you basically do pip install Panda, and that's all. And it will be available. And in your program, all you have to do is import that particular library, and that's all. All right, great. Now there we go. Next is your transformation. Next is your action after transformation. Action is interesting. It converts an RDD into a local value. All right. It brings all the data from all the nodes to a single node. Okay. And it can do it very gracefully also. Meaning, say for example, there is a function called reduce here. So this diagram basically shows you when you say action, it gathers the values from all the elements and brings it to a single driver application. All right. Now, a reduce, say for example, there is an action called reduce. What does reduce do? Reduce take your function and it applies this function again and again on the element until it, it gets all the elements converged to a single value. You remember our combiner? That's exactly the role of reducer here. Reduce basically take two elements at a time, combines them, and 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 then whatever is the result out of all of this uh, conversion of two elements, it is again applying the same function again and again. If you attended the combiner session, you will remember that. So I'll just go through it quickly. So we must be having something of this sort. Yeah. All right. So here, two values are being converted into one, and this is what reduce function does. So how does it do? You will have to define a function which takes two arguments and converts it into one. Okay. It returns this function should return a single value and take two elements, and the translation of those two values into single value is done by your function, and it will be called again and again on this RDD until it becomes a single value. Okay, and that's how it does it. So an action does not only run locally, it also run on each section of the RDD, meaning each node running the RDD. So first it will run on each section of RDD until one it converges into one, and and then it gathers all these four values back to the node, and then it applies this function again and again. All right. Difference between action and transformation. Transformation converts one RDD into another RDD, and action converts an RDD into a local value. And action is the one which causes the execution, which does something. Transformation is does not result in any execution. Transformation is like any step saying, okay, fine, you told me to transform, I will transform when you run any action. Okay? So that is the biggest difference between action and a transformation. So do you remember the way we discussed pig earlier? In pig, we had all these filter, this, that, group by this, and there was some action at the end of it. Action was dump or store. So it is very, very similar to that one. You are very correct, Santana. Thank you. And yes, you already said it. I shouldn't have described it. Great. Now, similar to reduce function, there is another b- similar to reduce function, there is another action called count. What does count do? Count again first counts the element on each node, and then sums up all of them and brings down to the local machine. It gives you the number of elements in your RDD. Okay, it it brings down all the elements in your RDD. It counts all the elements in the RDD and gives back you the result. All right. Collect actually gathers all the data from node and bring it back to the local node. It is opposite of sc.parallelize. Sc.parallelize took the local variable, convert it into an RDD, divide it into the cluster. Collect will get all the data, bring it down to the single node. Now take n will basically bring first n element of an RDD locally. Okay, so these are the few action. You can have more for more examples of action here, such as save as text file, opposite of loading the text file, and take ordered, meaning bring the elements in the order the way they are stored on the node, and take sample, basically give the sample of the total records. All right, and first will return you the first element of the array of RDD. All right, sounds good to you? Now, let's go through this exercise. This should give you, is the font visible or do I need to increase the font? All right. So imagine this. We had a lines of a file. We did sc.text file. We loaded these lines. Okay. We ran a translation called len. And what did it do is it basically computed line lengths of each one and generated another resilience dataset called line lengths. Okay, so that's what is going on. And then what we did was we executed a reduce function called sum, and this is what is going on. So should we do this exercise right away? Let's do this exercise. Okay, we our objective is first to compute line lengths and then do the summation of all the line lengths. All right, so lines is one object we had already loaded sc.txt file, and now let's do something like line lengths equals lines dot, who can help me now? Can anybody help me? We are trying to compute the length of each line, and remember, in lines, every element, lines is an RDD representing lines of our big.txt, and each line is an element of this array. So we can say, anybody, we want to convert each line into the, basically this is what we want to do. For each line we want to generate the line length. Okay, so what do we use? We use map, because we want to translate one value into another value. We say map and length. Okay, those who are not aware about length, let me show you what does this length function do. Whatever value you type here, it'll compute the length of that line. Okay, now ll internally would have converted each, would be containing the line lengths of all the values. Now you can see that I've just taken 10 records from it. So ll contains the length of each line in our lines RDD. All right. Now we have got this RDD. Now let's do the sum. Do we have sum function? Sum. Sum is not there. So let's define sum. Define sum. And let's call it sm instead of. Okay. So whatever two values you give it, it will basically sum it up. Okay. Sum is taking two values and converting that into one. Sorry, sm basically. We have to say sm, right? So it's taking two values and summing it up. That's all. Now this is a valid combiner or valid reducer function here. So we can apply the reduce function on top of our line lengths. Okay, so we say ll dot reduce, and say sm. So what will it do? It will sum up the line lengths of all the lines. And here will be total length equals this. Okay? Total length, total length is this one. Sounds good to you, right? Now what is going beneath the hood? What is going beneath the hood? Imagine that the same lines are spread across three nodes: node 1, node 2, node 3. First three elements are on here, second are here, third are here. The moment we did translation, this is LL, okay? So line length contain the lengths of these three elements. Here also three elements, and here also three elements. Okay? Afterwards, the moment we say reduce with our function called sum, what it does is it takes two element first and sum it up, and it becomes 20, and then again sum it up. So on node 1, the total length is 24 right now. And similarly, here it is 24, 14, and here it is 24. On these three node, now the value will be brought down to your local node, the driver node, our command prompt here. Now it will get 24 from node 1, 14 from node 2, and 24 from node 3. And now again the same function will be applied on these two values, and again these two values, and we will get the total line length as 62. All right, so this is distributed computing. This is how it divides your function across the cluster and gives you the result. So as you can see that your reduce function is first executed on each node until the value converges to a single value, and then that value all those values from a whole cluster are brought down locally, and again your function is being applied on the local node. All right, sounds good to you? Great, awesome. So here we have, all right, so now at this point of time we are well equipped to do the map reduce and do the word count problem using Spark. Okay, so let's do it quickly. I will basically try to write the code. So let me just pick up the stuff which we already have. So let me write everything again. So lines equals to load this data into lines. Next is we define a function to break down a word, each line into words, which is define two words. Okay, and we call it line two words. And whatever line we get, we basically return line dot split. Okay, so that is our function. Next thing we want to do is, now what will it have? We'll have each word as an element here, and we can also define map. Whatever word we get, or here itself we can do a couple of things. First, we can do line dot, right? And let me try to see. Sorry, this has to first, this will be run as a map, the flat map. Okay, it will convert a single object into multiple, so this will be a flat map. And the next is our word. For each element, what we want to do is, and here we can put the logic like if line dot length is smaller or bigger or whatever. As well, we can do lines dot remove special characters and so on. Okay, now map will convert each word into into key value. So it'll say word and value, right? So that's all. Now, first would be words equals lines dot flat map, and I pass the function called lines dot two words, right? Next is we call it the words key value equals words dot map, and let's say we call this function called 2kv. So we got words kv, which is basically nothing but each word comma 1. And next is we say group, and group equals words kv dot group by key, and we say that's all. So now this will group our data by the key, and afterwards we can simply do a reduce. We can say we can say we can say things like reduce by key. Similar to reduce, we have reduce by key, where the reduce function will be executed for each of the keys. Okay, and we say wc equals grp, the grouped data dot reduce by key, and there we pass our summation function. So our summation function would look like, okay, and we can say return this is v1 v2, and it will return v1 plus v2. Okay, so everybody with me here till here? Okay, so we have already written similar thing here. Okay, and we are saying flat map do something and it returns something, and then we say reduce by key, and that's all right. Now next thing we want to do is we take the results. So this is word count, and we want to say that please save the word count here, and before that we say collect or take 100. All right, so here I'm assuming here that everything is clear to you. In case there is a doubt, you can tell me which line number, I can explain that. All right, you can tell me the line number in this file. You can see these line numbers. Okay, so no doubt. So let's load this data again, although it's loaded again, loaded already, but let's load it again for the sake of clarity. Here we loaded the data, then we defined a function called lines to words. Okay, and check this function whether it's working or not. We say Sandeep Giri, and it should give us an array of two words. All right, makes sense. Now next is we pass this function, and now each line will be, if you say what was the lines, and we say lines dot count should give us total number of lines. So it has total elements of 1.2 lakhs, or you can think say 128k. And the moment we say flat map, okay, so we say words dot count. All right, so there are these 11, I think, yeah, 1.1 million this time, because each line got converted into words. So total number of elements are more after flat map. Next is we want to convert each value into key value. Okay, so let's test this function. So that's a beauty about these command prompt programs, that they let you test quickly, that help you test very quickly. If you are a JavaScript programmer, you must be using the the console in Google Chrome or Firefox, and that you would give you instant gratification in terms of whether your function is working or not. Similarly here also. And what you can do is, now let's generate key value pairs out of our each word. Now, just check whether it has done something or not. Let's just get the first from here. It says, yeah, the is there, or we can say take 10. Take 10 will give you the instantaneously the first 10 elements of this array. Okay. So you can see that each element is now the key in key value format, and how it got converted to key value function, the function we defined. Next is we group it uh, by key, and we have group. Now let's say group dot take, and it should have the same format. Now the sorting happened, and here you see that for each of the elements it has done the grouping. Here it's a blank array. U and double single quote means that it's a Unicode and a string with zero length. Here it's a Unicode value where the string is GAG, and so on. Make sense to you? So it has grouped the data by the key, but it hasn't really. It has basically brought the values together but hasn't done any operation. So let's define our function which will do some operation. So let's check whether our function does something. It basically sums up two values. Now we are saying we want to reduce group by a key. Okay, we say wc is this, and next is we can just check what is there inside word count. All right, so what did reduce by key did, it grouped the data was already grouped by key, and all it did is for each group it executed my sum function again and again on the values to reduce each array into a single value. Now you can see that this is what we have got. So what did we do? Take 10. All right. And yeah, but it has not returned anything. Reduce by key. Okay. So this is correct. Did we store somewhere? Group reduce by key, and the function is there. Group. Mm-hmm. Or we can just try to use this one. Yeah, our function is correct. And for some reason, it has not given us. Yeah, this is completely correct. All right. All right. Yep. hmm So let's try to save it as text file and then see. So it says already exists, and we say Fab 28, and we let's have a look at what is there. Oh, I think we were trying to. This is correct only. So this is where our data should be there. We can directly go there. So here we have two parts. Strange it is. This one is correct. So what is it that I made a mistake? Can anybody help me out here? So, so there where is my text file? Yeah. Here, if I say wc.take, then we get this, which is not correct. And if I say here group, this is my group, and we say this is correct because this has to be group only. And next is words kv dot take, then this is also correct. All we did here was we have this word's key value pair. Each word is represented like this. All right. And all we want to do is group by key. All right. I think we can simply say like this. Actually, yeah, this will be easier. I did a little bit of unnecessary stuff. Yeah, this is better. All right. So yeah. So here we can actually say map, and then we can sum up all the values. Instead of that, is everybody with me? So till here we were absolutely correct. What we did is absolutely correct. Just that we did couple of additional unnecessary step in this. We we converted the words into key value pair here. So words key kv contains word and a 1 as the key value pair. Next is either we could do this group by key and then again do map. Okay, here we could do map so that each group can be summarized in the map phase itself. Or we could simply say words kv and reduce by key. So, okay, we could simply say words kv dot reduce by key. That's all. So reduce by key will basically reduce by key is another transformation that is something you'll find strange because reduce by key is also a transformation, and it will basically execute your function on each of the keys for all the values in each of the keys. Okay, and WC will contain the data. All right. So this is clear to you. All right, great. So yeah, we unnecessarily did group by because reduce by key anyway does group by and then apply your function. All right. Any questions here? Okay. Now next is as we saw in earlier sessions also, time and again we needed to coordinate between Spark between various nodes. One map phase need to talk to another one, and that is not something very exceptional. Those kind of problems were difficult to model, and we needed to use things like zookeeper in order to do coordination between multiple nodes. Spark provides you as part of the uh, part of the core itself in terms of broadcast variables. So, in your code, while you start your process, you define something called broadcast variables, and these broadcast variables basically are available on each node. The moment you broadcast a new value, the same variable will get updated all across the cluster. Okay, so generally if you look at here, this function, whatever variable you define here inside the function, is no longer available, is a local one on the same node. You cannot communicate uh, between the multiple node using any of these variables because these variables become the local variables on each node. All right. Now, broadcast variables come exactly for the same reason. One node or any node in the whole cluster can broadcast. Okay, or you can look at it this way: inside your here you can say broadcast something. All right, you can broadcast something from there, and that broadcast will immediately will be available, that variable will be available to all the cluster. Okay, so that is the role of broadcast variable. Then it provides you something called accumulator. If each node need to update you with their progress, that I'm done with this, I'm done with this, or each node need to just send you the log errors, in all those cases they can use accumulators. In accumulators, the order in which the things are coming from each node do not should not matter to you, because there is no fixed uh, order in which you will receive the values. Okay, you will not receive the values from node 1 first, then node 2 and node 2 and node 3. No, it will be basically very spontaneous, and the based on various conditions of the network and node, you will get these things eh, to your accumulator. And that is why only the associative operation, the operations where the order in which things are done does not matter, in only in those cases accumulators are valid. For example, 2 plus 3 plus 4, whether 4 comes before or 3 comes before, it does not matter. So whether 2 plus 3 plus 4 is like this, or we have 4 coming first and 3 coming later, and still the answer is 4. So in all these circumstances, these are all the operations where basically the placement of the value does not matter. All those operations are good for accumulator. So you can do you can basically do things which where the order does not matter. All right. So this we have gone through already. And let's say we modify our base version of word count with few modifiers. First, first objective is that we clean up the words. We remove we remove special characters. We remove special characters from this, and then we use broadcast to tell each other that not to count these particular words. Okay, so those are few. So this example takes you through it. So first we broadcast that don't count a and the this that of is, and we broadcast these values. And here our broadcast variable can be anything: a complex object, a small object, simple object, anything. Okay, it has to be a single variable. And we also use accumulator in this. We initiate accumulator with 0, and then we we basically run our usual flat map and then map, and inside each of them there is a filter function we are defining here. In filter function, what we are doing is we are checking our value, each value against the broadcast. We are checking our value against the broadcast. All right. Okay. So this way we will be able to use the broadcast variable, as well as we are also telling that accumulator dot add 1. Okay, so that we have the progress reporting of the whole process. Okay, so at any point of time we can also print accumulator and show that these are the records that are done. All right, so this example takes you through the broadcast variable, where you can coordinate between various nodes. All right, so inside each function you can use the broadcast variable, and before we start we define the variable with certain value and keep on using it. All right, so after the break we'll go through a simple example of streaming. All right, and let's take a break of 10 minutes. All right, so can you hear me clearly? All right. So, any questions here? Yeah, yeah. Go ahead, Mark. Yes, I'm assuming you're typing. Okay. So I get that it spreads it across all the multiple nodes. Broadcast, send it out, and accumulator is like the actions accept across whatever you broadcast. hmm No, broadcast sends it out. Broadcast is the variable using which you coordinate. These are two different syntax. Using broadcast, you communicate. And then there is another thing called accumulator. Accumulator is like each node can report the progress to a central node. It's a one-way mechanism. So accumulator and broadcast are two different things. Okay. Next is yeah. All right. So is your question clear or is there something to it? All right. Great. Great. So everybody is okay with me with moving ahead and covering other topics? All right. Great. Great. And now, before I move forward, just have a look at this interview questions. And what I noticed is lots of us, when they are working on real life project or something, they are trying to solve a problem, they end up converting their problem to local one. Okay. So, uh, time to time, what happens is instead of using map or any of transformation or action, they convert their problem by using collect and then start operating locally. Okay, that hurts it really, really bad. The performance and everything, there's no point of using Spark then. Okay, and lots of users were making that mistake. All right, so have a look at this interview questions I had written some time ago. Okay, and I'll be adding more questions here as the time permits. And keep stay tuned to the forum and ask questions there. I'll try to answer as much as I can. And also, if you can answer some questions, feel free to answer or feel free to correct me if I have made a mistake there. All right. So yeah. So that was a really, really very crash course on Spark. And so we observed that Spark did the computational computations at a very, very fast pace because it utilized the RAM and the memory to a larger extent. Okay. Now, there are ways where you can specify that your RDD needs to be disk based or RDD needs to only load this much of data. So that is also there, but that would be too much for this session. And if those who are inclined to go forward into Spark into more details, that they can go ahead with their online documentation. That should be good enough. All right. Now let's talk about Spark streaming. Since Spark we found out that is fairly fast when it comes to doing operations. So some of the users, some of the people, some of the developers realize that they can basically convert and input data into RDD and then get the data be operated using Spark. And that way they can actually solve a streaming problem using Spark. Okay. So it is started like a hack in the beginning, but then it became a proper streaming API. All right. It was a hack, somebody's hack day project actually, which became a proper API afterwards. Now, so when we talk about Spark streaming or any streaming for that matter, so where in any streaming you load the data from various queues, Kafka, Flume, SDFS, ZeroMQ, Twitter. These are the fast data generation sources. Okay, so in case you are not aware about the message queues, do read about them at least once because they are a big pattern in a large organization. Say take a case of Amazon. Amazon have an internal queue called SQS. So all the applications push the data to this queue and other applications read the data from this queue. Okay. On the surface, this queue looks like a database, but in reality, it is the difference between SQS and the database is that this one provides you the data at a faster pace first. Second, the syntax to coordinate between multiple listeners for the same record. Okay, so imagine that I'll give you an example. So at Amazon, the project which I was working with was image optimization. So all the vendors are submitting the images. All the vendors across the globe keep on submitting the images, other information about the products, which are get displayed on Amazon's detailed website. So in case the example is not clear, feel free to ask questions. So at Amazon, there are lots of vendors who sell their stuff. Okay. And they also provide lot of images, content, and everything to be added onto the Amazon detail page. Now, out of all of these images, we need to pick up only one, which is best, right? And and basically this computation of the best is something very time consuming. We go through the image, we observe, we try to match it with other products and then see whether it's good or bad or how is the resolution. So it requires a lot of computation. So every time a vendor submits an image, we have to compare it with other existing images for the same product. And we have to do a lot of more computation. And this has to be done in real time. So on one end, lot of vendors are submitting data. On another end, we are listening to that data and reading from it and doing computations. And this computation has to be done really, really fast. As in, per second, we are expecting more than 10 records. And out of these 10 records, we have to filter out and see only the changes related to images. And afterwards, so this is a classic example where a SQS queue comes into play. And there could be multiple users listening to the same data at the same time. Okay. And the coordination between the multiple listeners to the queue is something which queue provides. Queue say in SQS queue at Amazon, what we did was the moment we take an element, the element disappears from the queue for next 5 hours. Okay, the moment we take an element from the queue, the element disappears for next 5 hours. In case you don't delete it, the element will reappear after those 4 5 hours. Okay. Why? Because you you could not delete it. That means that there could be a problem with your system, and this particular node has died which was processing it, so this element need to be processed again. So these kind of syntax is what makes a queue. We cannot use databases for such kind of throughput, right? These are mostly a queue supports a heavy writing, meaning you can write the data at a very fast pace into a queue and also read really fast. All right. So that is a queue. That is the definition of a queue. And whenever you are doing streaming, you would what would you do is you will listen to these data sources and do a lot of computation using multiple machines parallelly, and so that some elements go to one node and some element go to another and some elements go to some other nodes, and they all are functioning in parallel, reading from the same queue. Okay, so there are multiple ways to do such kind of processing. Okay, in my case, we built our own system similar to Storm. We'll discuss that later. But here, the good news is Spark could be very well used as a streaming handler, meaning it is not something like a queue. It's more like a computation on top of queue. All right. So the first step is to understand that part. So after streaming, the data goes into databases. The other important point you should note is first, streaming is not the Hadoop streaming we read. That streaming means we pass the data through a program. That's all. But this streaming is more like data coming in real time, and we have to operate upon it in real time. Also, please note that there is no such thing called real time streaming. Okay, we always break down the input into windows of time. Okay, whether half second, 1 second, 10 seconds, it is up to us. Okay, so whenever we are dealing in streaming, we convert the input data into something called batches of input data. We get the data stream, continuous stream, which is we are receiving at 1 millisecond or maybe lesser time, and we we keep on reading that data, accumulating it, and convert that into batches, and then operate upon each batch, and we get another output in the form of batches. So you can say that if there is a service which is receiving data frequently, and what we need to do is we need to do the word count every second, then we need to do the processing parallelly somewhere. If this word count takes a lot of time, if you are receiving 10 MB data per second, then you need to do this processing really really well. All right. So the way Spark handles it is Spark does the streaming. So Spark Streaming receives the data in real time, and then this streaming class, whatever we are talking about, there is basically a dstream class called discretized stream, and that discretized stream basically converts the input data into batches, and those batches go into the into as an RDD. So first element of an RDD would be the data from 0 to first second. Second element would be the data from input data from first to second, 1 to 2 second, and so on. Okay, so that is how the Spark streaming the entry point is what it looks like. So there is a class. Whole Spark streaming is around a single class called dstream. Dstream receives the input data, converts that into discrete stream, and converts that into basically a sort of RDD. All right. Now this is how it looks like. So dstream took the data, converted it into RDD at one time, RDD at another, RDD at another. Okay. So, or you can look at it this way. Here, dstream is essentially converting each second's window into a single RDD. Basically, as and when more and more data is coming, it's creating more and more RDDs in real time. For each window, it has created one RDD. All right. And what does it mean by Windows operation? At one end, you have data coming at a very fast pace, and then you're converting multiple data points into single window. That is called windowed dstream. All right. Makes sense to you? All right. On top of it, on top of it, Spark basically provides various Spark streaming provides you various kinds of more operation. The way we had reduce by key, it provides you the functions such as reduce by key and window. All right. So let's have a look at this example. So in this example, it basically connects to a particular service running at a particular port and starts reading the data from that service. Okay. It starts reading the data from that service. So here we are saying that create a window of duration 1 second, and out of that it will create something called a D stream output, which will basically be an RDD, a bunch of RDDs per second. Okay. Afterwards, you can do operation on these lines here, the lines which is generated. So if you look at this closely, lines is essentially a input stream being read from this port. Okay. So the continuous stream of data will be converted into windows, and those windows are being represented by lines here. And on these lines, we can do this function such as lines.flatmap, and it will do the basically whatever we did for RDD, the same things can be done here. All right. And after that, we had words.map, and right. So we can operate on we can run whatever we learned for our Spark in the same manner on top of the objects being created by streaming. Okay. So this basically generates what exactly are we trying to do? On each window of elements, we are trying to do word count problem. So on lines we did word flat map, and afterwards we did converted the line into key value pairs, word into key value, and after that we did reduce by key value. Here it basically would give us the results in the form of per second word counts. Okay, this would give us per second word count, and we'll keep on reading this data again and again and execute all of this simultaneously. All right. So this way, what exactly we did in this, if you look at it closely, instead of reading data from HDFS, we are reading the data from Java streaming context, which is which is part of the which is the basic the heart of the Spark streaming library. So Spark Streaming Library essentially provided you with the input, and rest of the data, rest of the things were standard RDD, standard parts of the standard part of the Spark. All right. Now, all right, all right. Now, next is, make sense? All right. Visually, this is what is happening. There's a live stream coming from the input, live stream coming, and you're converting into the RDD, and on each RDD, we are converting word counts like this. Okay. All right. Now, Sarju's question is Spark advantage over MapReduce? What is the benefit of Spark? In case of Spark, as you saw that the total response time was pretty fast, and in general, the way the number of things have happened, it is basically Spark does a lot of in-memory computation, which makes it faster. While MapReduce has been designed bottom up with the mindset that it will be handling the obscenely big data, as in uh, petabytes of data, and from every point of view, it was decided that it should not consume memory at all at any stage. Also, when it was designed, the way MapReduce was designed was was with respect to the batch processes. Okay, all right. So this is what we have now. The word count is for each line, for each window, we are doing word count, and it's being generated parallelly. All right. Now we have Apache Storm, which is which is also for streaming. So as we saw that Spark was designed for really fast computation, and afterwards Spark was designed for really fast computation, and afterwards we started using dstream to do the streaming because it was fast, but it was not designed bottom up just for streaming. But in case of Apache Storm, In case of Apache Storm, we basically designed the whole system bottom up. We designed the whole system bottom up for streaming. Okay, so Storm was essentially basically something which were designed at Twitter, and it was designed for really high performance systems. Yeah, I'm sorry, there was a little disruption. So Storm was basically designed bottom up for really fast computation at Twitter. Even before Twitter was born, during the time of the backtype, this was designed, and it was for it. Basically, it was benchmarked for 1 million tuple per second per node, and it is really highly scalable and fault tolerant and guarantees your data to be processed. Integrates with queuing and database technology the way our dstream worked. The There are many people who are using it. The If you compare Storm versus Spark, the processing model, in very simple words, when it comes to streaming, Spark streaming is okay, but Storm is really fast. It has been proven that over a period of time. Okay, but Spark basically, if you already have an infrastructure, if you already have installed Spark, if you have already provisioned Spark, then and your needs are that it's okay for you to have a latency of few seconds, then then Spark is great. If you cannot tolerate if you cannot tolerate the latency of a second, then you should go for Storm. If it is okay to be delayed by a second, then Spark streaming is good. All right. Right. So fault tolerance is, in case of a storm make sure that at least one record is handled at least once. Okay. And because when it has to be really fast and it has to be fault tolerant, the only way it would be to basically consider a element part of two windows, so that uh, it may not be missed out, the boundary should not be missed out. That is why there are chances that there could be duplicates. All right. if you compare if you compare the implementation programming API, and the origin of Storm was at Twitter, while Spark has been this and implemented in Closure, and this one is Scala. And Storm has been ported to almost all the prominent languages now: Java, Scala, Python, and others also. Batch framework integration is in Storm, it's not applicable, but in case of this one, we have Spark already. And the only other, the other downsides of using Spark streaming is that it has been invented recently, it has been built recently, so it may not be used. Okay, it may not be very. People may not accept it. The organizations may not accept it. All right. Yeah. So any questions here? No, actually. You can see here the resource manager Storm does not use Yarn. Okay. Storm does not use Yarn, and therefore it cannot be run. But Spark runs on Yarn. Essentially, if you set up a cluster with Yarn, because if you are installing if you, because if you are handling big data on your organization, there are high chances that you invariably would have HDFS, and hence you will have Hadoop, and hence you will have Yarn. And if you have Yarn already, you would like to go with Yarn if you do not need more than a second's delay. If you are okay with a second's delay in case of real time, then you will go for e- Spark. In case in case in case your latency acceptance is in sub-seconds, less than a second, then you would go for mm, Storm. All right. You can go for further reading on these URLs. So Storm is not yet compatible with Yarn. To run the Storm, you will have to do separate installations. All right. Yeah, I was telling about the company acceptance. So the first point here is Twitter has been in production since 2011, while Spark has come recently. So people would be little reluctant. But now the difference is not too much because both Spark is also like 2 years old and Storm is around 4 years old. Okay, so Spark streaming may not be acceptable right now, but now it should be okay. Earlier it was there was some because earlier it was very immature. Now it's fairly mature. But generally, whenever people are taking call in starting a project with some product, they generally have these apprehensions that which whatever is older one would be better, has been tested more. Yeah. No, we haven't installed Storm yet. Yeah. This was just to give you a comparison of streaming. Okay. So Storm was not really covered here. And just to give you a comparison of Spark streaming versus Storm, we have discussed it. All right. Now we have got this. All right. So if time permits us, then we will. The one thing which is left out is our Uzi. So let's go with Uzi once, and then we'll come back here. All right. So we were discussing that Uzi is a workflow engine, and we had discussed this workflow diagram. So is everybody with me? I'm going to jump back to Uzi, which we where we left off yesterday. All right. Great. Now, when you execute, okay, okay. Thank you, Mark. You continue with your work, and yeah, the reason I took this Spark earlier before Uzi was because Mark had to run, so he wanted to attend Spark right away. All right. So yeah, see you, Mark, in the next session. Bye bye. And yeah, rest of you have yeah, we'll stay tuned and we'll discuss Uzi and then we'll discuss a bit of NoSQL. All right. All right. Now we have. All right. So Uzi as a workflow, this is how it would look like. So the whole workflow should have the envelope one, the envelope node saying workflow app name equals this, XML namespace this, and after that you have to define an entry point. Entry point has to be some action's name, and then you can define an action here. Action name equals word count, and then you define MapReduce or whatever you want to describe. Okay. After that, after that you basically define what it has to do in case of error. Here, the let me increase the font. All right, here you can see this. So here's the workflow app, and here is how you define MapReduce. Okay, you have to tell that this is the job tracker, this is the name node. If you basically say dollar, it will take it up in from the settings, and that should be good enough. And here you have to define the all the arguments you pass to job when you say the what is your mapper class, what is your reducer class, what is the input directory, what is the output directory, and so on. Okay, and in case this map reduce finishes successfully, it should go to end, and in case it finishes, it gives an error, it should go to kill. Okay, that's a little mistake here. All right, now, so this is clear, right? This is how you define an action. This is how you define an action. All right, you can define multiple actions. So this was a single action where there is a starting point, there is a word map reduce word count, and there is an end point. That's all. But in case of you have a complex workflow, it could go something like this. So you start with first job, then first job forks out into second and third. And first job basically says that in case first job is successful, go to fork. And fork is going to take going to start second and third job. And the second and third job can say that when okay, go to join. Go to join. And then in the join, you can define that this is my final join. This is how the jobs should be joined, and so on. So basically, you can define a very, very complex workflow using this kind of description in XML. All right. So you can say that download my data, move it here, move it there, and so on. Okay. All right. If you want to go through an example, you can SSH there, and we have already uploaded. You can use the command line to execute it, or you could use the UI to execute any of the Uzi examples. So here you can have a look. You can go to the Uzi dashboard and define the complex workflow from the UI itself. You can say that go to workflow and create a workflow here. Say, give it a name of the workflow. All right. So this is my workflow, and let it load. Now in this, we can add all kinds of elements. Okay. We can take this map reduce and put it here, and then we can add all the properties. You can say my map reduce, and you can provide a jar. You can you can upload your jar. Okay. And our jar name was sg something. I forgot it. So maybe it was word count or something. Yeah, instead of writing XML, you can use this one. That's correct. All right. Yeah, SG word count is there. So this is the jar we are going to use. And then in case we want to create a directory and make a directory before executing this, we can do that. And we can also keep on adding properties. And in the properties, we will describe that what is our mapper name. Okay. This is our mapper class. Okay. And yeah, this one is not something correct. We have to specify by ourselves. So it would be sg dot mapper. What was that mapper driver? My mapper, I don't remember, and so on. Right? So once you save it, you have a MapReduce class here. And after that, you can maybe you if you instead of normal MapReduce, you wanted a streaming, you can use a streaming job. Okay, you can say this is some streaming, and here my mapper is WC, or my mapper is, what was our mapper? SED substitute space with new line. That's our mapper, and reducer might be unique minus C, and we can say the files which we want to operate upon, we can tell that, as well as, okay, the input files, and properties will the properties will contain the input directory and all, and then we can save it, right? So similarly, we can execute a Java program whatever we want on the cluster, and you can use pig script. You can say pig, and then we can specify a script full. We can upload our script here and use that script. Okay, and we can also execute a Hive script. So we can say Hive, and then specify the location of our Hive script. And Hive script or Pig script is nothing but all the Hive and Hive commands or script commands bunched into single one. Now, if we want to do a scoop before starting the data, let's say we want to import the data, then everything after scoop command, we type it here, export this, and we mention it here. That becomes our scoop script. And shell script is something, if you want to execute a shell command, then you can specify it here. Also note that if we are going to run if we are going to run this workflow using something called a coordinator. Now, if you run something called coordinator, it is also a service and it will run on any of the node, not necessarily on a particular node. All right. Similarly, if you want to copy the data, then you can use either distcp or fs. Fs also helps you copying the data, and so is the distcp. And if you want to send an email, you can use email workflow or sub workflow. Okay, and or generic workflow. All right. Say you created one workflow and you want to call it from another one, you can use sub workflow. And one more thing I forgot to tell you, let's say if you want to execute these two parallelly, streaming and MapReduce, you drop MapReduce onto streaming and they will go into fork. So these two will be executed parallelly. All right. Make sense to you? You can add it here. What does this need? Basically the name of it and so on. Right? This is the way you can define the workflow. And what does it mean? Basically, just after start finishes, streaming and my MapReduce will start executing in parallel. And that's all. We can save it back, and that's all. Our workflow is now saved. We can either submit it or go to my workflows, and then we can do a schedule. We can specify that it should be run at this period of time. Okay, this is my coordinator. I define a coordinator, and after I define the coordinator, I can define the time when should be when it has to be start, and when should it does it have to repeat at some time or not. And I can also define certain input files, based on which, in case those input files have changed, only then it gets executed. All right. So that is about our that is about our Uzi. So any questions related to Uzi here? Make sense? No? Great. Great. All right. All right. So actually we have half an hour left, and we have actually the whole course only has maybe a total 30 more minutes work. If you want, we can finish today itself, and next session we can keep for the discussion purpose. All right, let's see whatever we can cover, and next session we can keep for discussion purpose. All right. All right. So let's just go over various available NoSQL solutions, and then think about various uh, various situations. All right. So there are hundreds of NoSQLs out there. We only discussed HBase, and there are hundreds of NoSQLs out there, and it's always a problem of there's always a confusion which one to use. So one is Redis. Redis is an in-memory database. Although the whatever data is there in memory, it is saved on the file, and it can basically the whole database is always has a copy on the disk. But but it, the whole database is also in the memory. Okay, that means that you cannot handle the data that goes beyond the memory size. If your data is small but you require a really fast computation, meaning you do not want to involve the disk at all, then Redis is a brilliant solution for you. Okay, and specifically if you want to write the data very fast, if your data is changing extremely fast, so changing the data whether in SSD or any hard drives is a very big process. It takes a lot of time, and therefore in those circumstances Redis will be your best solution. So your data should fit into the memory, that is the only clause. And the examples of the usage of Redis could be real-time stock prices, real-time analytics, leaderboards as in last 5 hours, who has been the fastest player across the world in the gaming when people are playing the mobile games and all. So in those cases, Redis becomes a very good solution. And when did we use Redis? After our recommendations were finished, we loaded this data into Redis so that while serving to the end user, the our J2EE application can quickly query Redis for the recommendations. And that is how we were using Redis, because Redis is really fast when it comes to smaller data that can fit into memory. Okay. So Wherever you could use memcached, if you have used memcached for running your web service, if you run a website, a PHP website, and there's a lot of data, okay, if you're running a website and you want to cache lot of data which is being served from your database directly, then you would generally use memcached. So, and memcached has been used like a data store for quite some time. So wherever you use memcached, you could use Redis. All right. Next is MongoDB. And okay, when you want to store your data in the form of objects, then MongoDB is a good database. Okay, when you have a lot of dynamic queries, lot of when you prefer to define index over these kind of complex objects, then MongoDB can be a good idea. Okay, so if you need really good performance on a object database, then MongoDB could be good. And so the other thing is, in case, as we talked earlier, in case you are running a website and you have to serve these pages to the end user, in case you try to combine these tables, it becomes very, very restrictive. Instead, defining an object is far more simpler in JSON as compared to joining various tables. And every time you are including a field, in case of MySQL or any of the databases, it becomes too restrictive sometime, that that you want a kind of a database for which a field change does not matter. And that's where the MongoDB comes into play. Okay, so in MongoDB you store data. So I think I don't have MongoDB right now. Yeah, I don't have MongoDB right now. I think maybe locally I will have launch CTL, and I can see list. There would be MongoDB somewhere. Okay, so it's not really running. All right, it's not running, so I cannot show you the demo right now. Never mind. Yeah. So basically, when you use MongoDB, you store the data in the form of object. So instead of a row you have objects. Okay, this object can have either normal things like my field name is John, last name is Smith, age is 25, or it can have further complex objects such as address is this, and it can have further things like address is colon, and then under this there are three level of objects. So in general, the MongoDB can tolerate 100 level of nesting. The basically brackets inside brackets up to 100. Okay, up to 100. Yeah. So it is always a JSON object. And you can create the indexes on these objects saying, please, please create index on address dot street address, so that you can say select star from these objects and get me the objects where address dot street address equals something. All right. That is how you generally filter the data. So, if you need indexes and you need to store these complex objects and your MySQL is holding you back because you cannot add more columns, then MongoDB could be really brilliant solution there. Next is Cassandra. When you have to store huge data sets in almost SQL format, then Cassandra is a good solution. All right. The only thing is you have to set up the Cassandra from scratch independently. Okay. If you already have HBase and everything installed and data is always already there, you will like to go for HBase instead of Cassandra. But in case you don't have an HD Hadoop cluster, then Cassandra could be a great solution for you. All right. The IoT data which is coming from various places can be stored in Cassandra, and web analytics to count hits by hours, by browser, by IP, etc. The transaction logging, data collection from huge sensor array, meaning the IoT, okay, Internet of Things data, could always be used, uh, always be stored in Cassandra, and Cassandra would be a good solution for such problems. Okay. So whenever your data does not fit on one machine and still you want MySQL kind of an interface, SQL kind of interface, then you go for Cassandra. And it provides you things like Hector. Hector is a ORM solution on top of Cassandra, just like Hibernate. So, and Cassandra also provides you a SQL like query. All right. Next is HBase. HBase has billions of rows and millions of columns. When you have such kind of data where you have billions of rows and millions of column, you generally settle down for something like HBase. Okay. It is best if you use Hadoop and HDFS stack already, then you go for HBase. If you don't have Hadoop and you don't have any plans to use Hadoop, then you go for Cassandra in the same circumstances. All right. On HBase, you can search engines. It can be used for search engines. You can analyze log data. Okay. Basically, you create two-dimensional tables which don't generally require joins. All right. Same as HBase, there are accumulo hypertable, but it's not those. Accumulo basically gives you cell level security on top of what HBase is. So if you can create the what do you call the handlers in case of HBase, then you can also provide cell level security. Okay, so yeah, you can have a more details onto this URL. This blog gives you a far more detailed analysis, and you can have a look at there. All right. So any questions here? All right. So no questions. Santana, Sarju, Anand. So actually, I have not planned any demo for Hadoop install or admin or Zookeeper, but easier thing would be, let me just I'll just tell you what exactly I did. And yeah, so let me, yeah, actually I'll have to go through email somewhere. All right, so I'll just walk you through this. Maybe you can go through it later when you have time. So the way I had installed the cluster, I'll just describe that, and that would be probably the e- easiest way. Yeah, yeah, I'll share that file. Okay. So let's say you wanted to install Hadoop on these machines. I'm not really prepared for this, but let me try if I can explain. Okay. So the way I had set it up, the cluster was, first I copied First, I copied the SSH key on Hadoop 1 and Hadoop 2 and Hadoop 3 and so on. This way, this way I did not have to provide my login ID again and again and password again and again. Okay, this establishes the trust in the beginning. Okay. Next is I installed the basic utilities on the machine. This is I have basically first installed the operating system called CentOS. Okay. So after that, I did these basic things which are required. Now on one of the nodes, all I did was I installed the Ambari server using yum install Ambari server and Ambari agent. So I installed Ambari server and Ambari agent on say Hadoop 1 first. Okay. Next thing I did was I said Ambari server setup. Okay. And then it will take me through a full bunch of wizard and will set up the Ambari server on Hadoop 1. Okay. And once that was done, I said Ambari server start, and it started Ambari on Hadoop 1. All right. Next is I installed something called Ambari agent on both Hadoop 1 and Hadoop 2. Okay. And while after installing Ambari agent, we informed Ambari agent to the Hadoop 1.no big data, telling that this is where our Ambari server is. And then we said Ambari agent restart. Once that was done, I hope I'm not disclosing some password. All right. So yeah, I'll have to cut the things from here because this one may not be shared with people. So I'll send you this separately. And okay. And here what I did next was I, after telling Ambari agent that this is my server, I restarted the Ambari agent, and this I did on all other nodes. On Hadoop 1, this is the only thing I did on Hadoop 1, while this part I did on all the nodes. Okay. And at the same time, I had copied basically I had copied uh, the SSH key from Hadoop 1 to all the machines. Okay. Hadoop 1 to all the machines, and that made sure that everything would be, Hadoop 1 will be able to connect to any of these machines and install things. Okay. All right. And So you can see that basically the simple in simple words on actually a better way would be to describe it using here. So this is our Hadoop one. Okay, this is Hadoop one, and this is say Hadoop two. This is say Hadoop two, and so first I Ambari install Ambari server. Next I do is Ambari server setup, and then start Ambari server. These are the first thing I do. Next I do is on this machine I install Ambari agent, add it Ambari agent ini, and then start agent. Now once that is done, I go back to I and at the same time I copy the the SSH key from Hadoop 1 to Hadoop 2. Which means when I do that, which means Hadoop 1 can connect to Hadoop 2 at any point of time and execute any command. And once that is done, I open HTTP Hadoop 1 8080 and then start the provisioning. Okay. And in the add host, all right. So this is what you do generally. Okay. Yeah, that's correct. So provisioning is pretty much GUI driven, except for this initial work. Rest is just GUI driven. And this will basically install everything starting with Hadoop till Zookeeper. Except for Spark, everything will be installed. All right. So now let's discuss. We have got 4 5 minutes left, so we'll just discuss quickly about the project, and then we'll rediscuss it on the next Sunday. Okay. So if you go into my courses, all right, and session number 11. So the problem statement is so the problem statement is do the sentiment analysis for a movie. Okay. Now you can do the sentiment analysis for any other movie than Iron Man. We will just go for this basic one. You can this is a very primitive strategy for sentiment analysis, and it is up to you. And we will be using Hive. It is up to you what exactly do you choose, whether you want to go with another strategy or you want to change the whole setup completely. It is absolutely up to you. I can suggest you few deviations which you should go for. You can change. Right now the current approach in this one is we give -1 to negative keywords, 1 to positive, and 0 to neutral. And based on that, we try to judge the negative positives. You can convert that into odd or even, and you can try to figure out a better strategy over there. You can use pig instead of hive. Third is you can use different algorithm to compute the sentiment. Fourth is you start afresh for a different movie or a different topic, at completely different topic. Okay, and you can use your own Flume pipeline to download the data. Right now, I have already downloaded the data for you. You can use your own Flume pipeline and set it up by your login ID and then download the data. Okay. Next is you can create your own program to download data from Twitter, maybe Python. One of our student has done it already. And next is use some other mechanism of displaying the data such as D3JS or Tableau or maybe BERT. Right now we will be using Microsoft Excel. All right. So you log in into Hue and locate the data. The data would be located here, and and basically go into Hive folder in the upload. There you will see the Hive query here. I'll show you that. So understand this Hive query. This is basically going to query the data and convert it into the the analysis we require. Okay. So here let's go through this query. First we create an external table called tweets raw on top of our data which is lying over there. Okay. Our data is lying here called tweet in this folder, and this data is zipped and is in the form of JSON. To load the data in JSON, you use the JSON survey, and therefore, before you start the process, you add this jar. This jar is also available as part of this folder itself. Okay, this jar is something which is available in public for everybody who wants to use who wants to load data in the JSON format in Hive. Once you have loaded the data, you load dictionary, you load time zone map, and then you create a view called tweet simple where you convert the date into from a string to a timestamp. Okay, and also afterwards you do a outer join on time zones map. Basically convert time zones is required so that we can convert the time zone into country so that we can see the country wise analysis, and this is where we are doing this. So we are joining tweet simple with time zone and reducing the country. Okay. All right, and here we create the views L1 and L2 on top of this data, and basically we are breaking the sentences into words, and after that we are going to uh, use that to compute the polarity. Here we do, after joining with dictionary, we are joining with dictionary to compute the polarity and by comparing the word. So this way we join the table here. You can have a look at here. So this way we compute the polarity of each word, and once polarity was create done for each words, we again grouped it by ID of the tweet so that we can sum up the polarity for each tweet and compute whether it's negative or positive. All right. So if you see here, basically we are summing up the polarity, and that means that if there are two negative words, it is going to become more negative than positive. All right. So you can change this strategy into even and odd. All right. That will give you the better results. And once this is done, you can go for you can create a final table while translating positive into 2 and negative into 0 and neutral into 1, and that's all. So there you go, you got a clean data at the end of it. And now you next step is here. Next step for you is install the Excel driver from Hortonworks, and then try to load the data from Hive. You can basically, after you install this Excel driver in your Microsoft Excel, you can directly connect to Hive from inside of your Microsoft Excel, and then represent the data in this format. So go through this document step by step, and you should get a fair amount of idea on what needs to be done. And let's meet on next Saturday to if you have more points. Okay. If you are not joining next Saturday, drop me an email. Okay. So we'll next Saturday there is not a single agenda at all. Next Saturday I've allotted for the general discussion. If you have any questions, any questions, you come up with that and we can discuss. If you're not coming for next Saturday, let me know and we can plan accordingly. All right? Are you with me? Right now, this example I have gone through is in Hive. In case you want to do it in Pig or any other, it is up to you. And you want to break down the steps into multiple technologies, that's also up to you. Or you want to use MapReduce as in Java MapReduce for this, it is completely up to you. Okay. This is just one approach I've gone taken you through. All right. So see you next Saturday. In case you are not coming next Saturday, let me know if you have no points to discuss. Just let me know upfront. All right. Yeah. Yeah. See you next weekend. And thank you very much. Bye bye. Have a nice time. Yeah. All right. Bye.